So, hello everyone. I am Erik. I work at Collabora on the graphics team, and I will be talking about a not really hardware enablement project. I had an accident yesterday, and hit my head, so I've moved my slot, and I will, as a result, probably go a little bit slow and we might not make it to the end of the presentation. But yeah, so that's me. So yeah, the goal here in general is to implement OpenGL on top of Vulkan to make a simpler graphics stack in the future of the Linux desktop. So there's a few other attempts at this out there that already exists. Think Silicon has made something called Glove. It only implements OpenGL ES 2.0, and the CLA requires a copyright assignment there, so which can be tricky for some companies to work with. Google has Angle. They again also implement only OpenGL ES. And then there's something called VKGL, which targets OpenGL 3 core profile, so it's not going to do legacy OpenGL versions, no fixed function or anything like that. And this is a pretty slow-moving project. It's a spare time project for a single developer, and it has a really long way to go before it can be very useful. So for solving this, there's nothing really out there that fits well. So did I go the wrong way? Oh well. Yeah, so I guess I swapped these slides. I'm sorry for that. Yeah, so why we want to solve this is that OpenGL is a requirement for supporting desktop applications. It's a pretty dated API. It's been around since 1992, and the hardware has changed a lot since then, and so has the software world. So there's a lot of things that OpenGL isn't so well suited for. My work came out of virtualization, so being able to use GPUs in virtual environments. I'm working on Virgil and Mesa for this, and there's some problems with that we're trying to circumvent by seeing if this venue works or not. Vulkan is also kind of becoming more and more proven technology, and it's pretty clear that it's becoming the dominant graphics API going forward, which means that OpenGL has a little bit of a less bright future, and it's better for the graphics community if we can all kind of work on one API rather than multiple ones. But as I said, we still need to support all the applications that use OpenGL currently. Yeah, and there's some other use cases that can be enabled by this work. For instance, mobile platforms that support Vulkan can get full OpenGL support, which they don't currently have. So my solution to this is called Zink. It's a Mesa Gallium driver that takes the Gallium API calls and translates them into Vulkan. It's currently in what I would call an early kind of out-of-tree prototypes stage. The driver works reasonably well. It supports OpenGL 3.0 on both RADV and ANV, so the open source in Mesa, AMD, and Intel drivers. We haven't tested much on anything else. Some people tried to get it working on NVIDIA, but there were some difficulties with the lack of DRI2. Dave Airley has jumped on this and started contributing a lot of really cool features. The driver is written in a pretty kind of like naive, happy-go-lucky approach to kind of see what could possibly go wrong, and it turns out it works a lot better than I feared. And I can run a lot of games and other demos, applications with a pretty usable performance. I'm not going to talk much about performance because we haven't focused that much about that on that. But for some simple benchmarks, I get roughly half of what i965 provides, and that's with some pretty not great stalls that we're doing kind of to please the Windows system. Yeah, so currently I'm taking a little bit of a step back and kind of re-engineering it a little bit, because a bunch of the early design decisions I've made turned out to be mistakes. So I'm trying to build a smaller feature version of it that I can upstream in Mesa, and then kind of build more of the features on top of that again. Yeah, so it's a Gallium driver. For those who don't know Mesa, Gallium is a system that takes OpenGL calls and kind of translates them into a more low-level API. And yeah, Zink will kind of take that and translate that to Vulkan. Yeah, and communicate with some Windows system. This is the software Windows system, which is not good. Where we have a hardware, like a DMA buff-based thing as well. And here's a rough overview of how draw calls kind of, or the data flow of the driver. So there's, for instance, a compiler that feeds a program cache, and there's a pipeline cache that takes in render passes and creates frame buffers, and yeah, feeds that into command buffers. Yeah, so we're doing the shader work with a NUR, which is an SSA-based compiler IR in Mesa. Translates that into SPURV, which is the Vulkan shader IR. I chose to go that direction rather than something like TGSI, mostly because SSA to SSA is or seemed to be a great fit. It turns out to be a little bit harder than I thought because of some annoying differences in how they treat some of the fundamental SSA constructs. I will talk more about that. It's written as a reusable module, hopefully similar to we currently have a SPURV to NUR, so it's kind of written in a somewhat similar fashion. And I'm hoping that with that maybe we can make an in-tree GLSL all the way to SPURV compiler in Mesa. This isn't an important goal, but it seems neat to be able to do that without pulling in other compilers. Maybe we need to pre-compile some shaders, for instance. It does not generate awesome code. It seems the Vulkan drivers on desktop kind of make up for the bad code we generate by optimizing it afterwards. But I fear that this is not going to fly on mobile. Mobile drivers are probably less eager to spend CPU time on optimizing the code first. Yeah, so I'm going to talk a little bit now about the different difficulties we met. Some of these have solutions, some of them have ugly hacks, and yeah. Yeah, so control flow, we don't support it. Pretty bad. This is one of the kind of big ticket things that needs to be fixed, I think, before I can upstream it. Yeah, I have some prototype, but that kind of crashes and burns in some cases. It's trickier than it sounds, and the reason for this is these SSA differences that I talked about. In NUR, jumps can occur from anywhere inside a basic block, which is a very creative way of defining a basic block, I think. So for instance, yeah, NUR jump and return, break, continue, these can all do it, and some intrinsics also have implied control flow modifications like discard. In SPURV, all of these terminate the basic block, and that means that addressing phi nodes gets pretty hairy. It's probably not super duper hard to solve, but I think I'm going to have to accept not a direct translation here first, and do something a little bit clever. I haven't really spent much thought about this after kind of hitting this wall. Yeah, another problem is that the SSA values of NUR is typeless. They're basically just a bucket of bits, which means that we currently just bitcast everything into and from uint. This creates a lot of needless instructions in a lot of cases, and yeah, it's not great. Jason Ekstrand of Intel has been nice enough to create a prototype for like a kind of a scanning pass that finds out which casts can be removed and kind of replace the different SSA values with typed versions. It doesn't work for all of the stuff, but it doesn't need to. It's kind of only needs to do better than nothing. There's still, yeah, some constants are still problematic with that, but I can probably extend it and stuff. I haven't tested this pass yet because of time restrictions. Yeah. Then another thing that needs to be solved that we're not doing awesomely is how to bind shader resources to the shaders. And for those who don't know Vulkan, the way you address resources or you bind them is through descriptor sets. So you have a set of, like, you can have n descriptor sets, and they have kind of indexed resources inside of them. We currently just push all of this into one big descriptor set, which is a pretty easy approach, but it's might not be great from performance point of view. Especially the Vulkan spec suggests that this is not a good idea. We stole that idea from the XVK, and it seems to work okay, but at some point we should probably look into doing this a bit more properly. And I think making a descriptor set per stage, per shader stage, makes this easier. Then we will get much smaller indices there, and that seems good. Yeah, and then we also need to have, as you draw, we need to deal with the descriptor sets. Currently, what we do is we create a huge descriptor set pool, and just allocate from there until the allocation fails. Then we flush the GPU and wait for the GPU to finish and reset the pool. That's obviously not a great idea, and it causes some validation errors and some frame rate hiccups. So it's probably better to have multiple smaller pools and keep track of how many descriptors we've used from there, and use some fences to automatically wait if the next thing wasn't finished yet on the GPU. Yeah, for those who don't know what pipeline objects are, they're an object in Vulkan that encapsulate pretty much all of the draw state. These are relatively expensive to create, so we try to cache them and keep them around for the next time we try to use the same draw state. We currently just do that kind of naively, put them in a hash map, but in the future we want to move to building a non-optimized version of this eagerly, and then kind of have a background thread that creates optimized pipelines instead. This is what the XVK does, and it seems to work well for them. If any of the Intel driver people is listening, it would be great if you guys started respecting the disable optimization bit for this plan. Yeah. Anyway, so this whole thing is similar to variant caching, and it's not really a big question what to do here. Yeah, and we need to also deal with image layouts, which is one of the big differences with OpenGL. For those who doesn't know quite what that is, that it's kind of like it's a hint to the driver what you're going to do with an image. So you can, for instance, be set in a state where you can only do rendering to it, or you can only do texturing from it. And generally speaking, these optimizations, or these might have some optimizations on the hardware level, where they're faster at being accessed. We just use the big hammer called layout general and translate to that as early as we can and just keep them there. There, every operation is allowed, but the performance isn't necessarily great. This is not a big problem for us yet, mainly because we're mostly CPU limited rather than GPU limited. Of course, depends on the application, but yeah, it has some nasty implications with raciness, with multiple context, where the problem is that the resource has different, like the resources can be shared, and the context is the only one who kind of sees when the transition happens. So we need to insert some fencing or something there to make that sure. We're not doing that. I haven't tried anything that does multiple contexts yet. Yeah. In addition to this, Angle is doing some really cool work of building something called a frame graph, which is like you kind of build a timeline of what's happening with things, and then issuing things so you can move your image transfers as early as possible, which is supposedly better for performance. I can imagine we can do, like, just steal their ideas there and something. But this, I think, comes down the line a bit from where we're at now. Yeah, and so uniforms is also kind of a little bit different. In OpenGL, you can have, like, freestanding, like, default uniforms that, or a default uniform block. And in Gallium, this is a little bit, yeah, they look different from the IR and stuff like that. We basically just do a shader, a compiler pass that transforms them into a uniform block. There's already some stuff in Gallium to do this by default, but we can't use that for some technical reasons yet. Yeah, there's some difficulties here. It's not really that interesting. I'm going to just go on. Yeah, and then one other issue is that we're depending for some OpenGL 3.0 features and stuff like that. We depend on some ext extensions and stuff like VK-ext transform feedback. I'm not so sure we can rely on that forever, and probably not at all on mobile. So we need to rethink some of these solutions. I kind of can envision some of this stuff being done with a giant compute shader that you inline all of the different shader stages apart from the fragment shader into, and kind of build some queues. Basically re-implement the GPU pipeline compute shader. Some people have done this before with CUDA, and it's pretty successful. So it is an option, but maybe it's better to do some more targeted, smaller things for simple features where we maybe not fully support the spec, but or get applications running. We'll see. Yeah, there's other extensions than that has the same problem. So yeah, we're currently supporting OpenGL 3.0, but there's a little bit of an asterisk there. There's some features we're not missing. Most of these are fixed function kind of details. Polygon mode is different in Vulkan and OpenGL, where in OpenGL you can specify a different polygon mode for front and back faces, and on Vulkan you can only support specify one. So we just currently issue a warning if they're different, and use the front face state for that. I haven't seen any applications fail with this, but as we test more applications, I'm sure there's some CAD applications that aren't going to render correctly. There's several emulation paths we can try, something like drawing all of the back faces first and then all of the front faces, and kind of assume the ordering isn't important. We can write out the primitives to a buffer and like stream it out, and use a geometry shader to construct triangles afterwards, maybe. I don't know. It's a pretty low priority issue to fix. Texture borders are a little bit different. In OpenGL, you can have arbitrary texture border colors. And in Vulkan, there's 3 different ones you can have. Transparent black, and opaque white. We just hard-coded as transparent black all of the time, and I've only seen synthetic tests give any problems. But it's totally possible to do this by injecting some shader code. It's not actually that bad to do that, but yeah, it's not awesome. Yeah, if needed, we could implement like some extension to support more modes, but I doubt it's going to be important. Yeah, point size was you can either in OpenGL you can either write the GL point size output in the vertex shader, or you can set fixed point size for the whole draw call. We need to like have some in Vulkan. You can only write the vertex shader. We haven't done any forwarding there of that state. It's kind of boring code to write, but it's relatively easy. And I think also some of the other drivers that are working to be upstreamed are going to need something similar. So maybe we can work with them on a shared solution. Yeah, alpha testing. It is, in theory, very simple to implement, but it requires control flow, which we don't support. Yeah, so this. Yeah. If we fix the control flow issue, this will go away very quickly. So currently, we support OpenGL 2.1, like as the lowest set of features we can support. It requires Vulkan 1.0 and a bunch of different physical device features, which we don't test for, so yeah. Probably will before we land this driver, but maybe with an override or something so you can run things even if it's not perfect. Yeah, and OpenGL 3.0 requires 2 more ext extensions. Those are both enabled on RADV and ANV, so on both of those drivers we get 3.0. I had some slides about future versions, but I decided to cut them. They're in the slide deck if someone wants to download it and read some more. It basically goes through which Vulkan features we're going to require for all the way up to 4.6. Yeah, so in the future, there's a bunch of more stuff to be done. The biggest problem is that the compiler is not as great as it could be. I'm not really a compiler guy, so if someone who knows compilers would like to help out, that would be awesome. Yeah, and then it's like fixing rendering issues in applications and upstreaming in Mesa. Yeah, and after that it's like cracking away on the newer OpenGL versions. Currently, I'm kind of the bottleneck here, and I'm really, really sorry about that for anyone who wants to contribute. I would be very willing to have a discussion on fixing that somehow. So yeah, any questions? 2 minutes. 2 minutes, so 1 or 2 questions, I guess.
Anybody? How viable will it be to take this project and run it outside of the Mesa framework, I'd say? Like if you want to, I know Apple is dropping OpenGL support on their macOS, so it's only a matter of time before we need to do something like this. How reliant are you on the existing code base from Gallium and other, I mean, or how viable would it be to ship something like this outside of the free desktop environment?
So I think if I were to have a crack at this myself, I think I would have gone the other way around and gotten Mesa to run on macOS. I think there are like built like CI checks and stuff in Mesa for macOS. I think it works. And something very similar to Zink, I think, would be needed, but that outputs metal instead. There are some people who have.
There's already something for Vulkan to metal, so you can fight it.
Yes, Molten VK is interesting, but I think layering emulation on top of emulation is a way to insanity. Like, if someone wants to try it out, they're free to, and you know, if they report some bugs, that's great. I will, you know, have a look at that. But I don't have a Mac. I'm not gonna give this a try. Yeah. All right. Any more questions?
Quick one. or not at all? Okay, thanks a lot.
Also, we're hiring.